So here we have a data that shows the blood pressure, systolic blood pressure before and after an hour of meditation. And you want to know if the overall blood pressure went down afterwards. I mean, the data seem to suggest that because you see more numbers going down than going up. But we have to actually do the hypothesis testing to make sure that it's true. And the way we do it is by either using the t-test or the Wilcoxon rank sum test. But there's a big difference, right? You can use t-test only when what?
Normally distributed.
Yeah, if the data is normally distributed. If you have some strong evidence that people's blood pressure is overly following a bell curve, then you can use this. If it's highly skewed or it's just totally chaotic, then you can't use this, right? Okay, so assuming that it's normally distributed, that means this means I can use t-test. All right, so what you want to do is plug in those numbers into L1 into your calculator and do one variable statistics, and that gives you X bar as what?
1.
Is this 1? Oh, yeah, that's simple. Okay, and then your SX is?
4.055.
4.055. Okay. And our N is 10, so degrees of freedom is? 9. Okay. With all these given information, we can start the 4-step process of the hypothesis testing. So step 1, what do? H0 is that the two means before and after are the same. Or this is also saying that difference, which is mu1 minus mu2, is 0. But the alternative is that mu1 is bigger than mu2. In other words, the blood pressure before meditation is higher than blood pressure after, which means that D equals to mu1 minus mu2 is bigger than 0. That's alternative. Okay? And you're really doing the hypothesis testing on the difference. This is a paired test. So is this a one tail or two tail?
One tail.
It's a one tail, right tail or left tail?
Right.
Right tail, because D is bigger. Okay, so we have step 2. We need the right tail, and because we need the t-test, we have to do inverse t. Oh, I should really say alpha. Let's say our significance is 0.05. Okay, so since it's right tail, we have to put 0.95 with degrees of freedom 9. Can somebody give me this answer?
1.833.
1.833. Right. So that's going to be our critical alpha value. Okay, or really to follow the convention is T1 minus alpha. Because it's 0.95, which is 0.05. We plugged in 1 minus alpha in here, okay? All right, now step 3, we have to calculate the test statistic, which is T equals to the difference, right? So your X bar, this thing, minus 0. Because this X bar is your sample value of the difference, and 0 is what would be true if the null hypothesis was true. And then you have 4.055 divided by square root of 10. Okay. So what do you get? You get like 0.7 something?
0.779.
779. And that is not in the rejection region. So what's your conclusion?
Fail to reject.
Failed to reject.
Due to insufficient data.
Yeah, so the data does not support rejecting the null. So it just means that this data does not support that meditation decreases the systolic blood pressure. Okay? Does that mean meditation does not decrease blood pressure? Is that what it means?
No,
What does it mean?
we don't have enough data.
Yeah, we don't have enough data to say whether it decreases, right? So if you really think that, if it was really true that meditation decreases blood pressure, what's needed is 10 people is probably not enough. You need 100 people to actually get something meaningful. Right? The difference is not big enough to be figured out in just a sample of 10. Right? Okay, so that's when it follows the normal distribution. Okay, B, assuming systolic blood pressure does not follow normal distribution. In such a case, you're forced to use a non-parametric test. And one of the non-parametric tests that we learned was the Wilcoxon signed rank test. We also learned the signed test, but that's not good enough. So whenever you can, you have to use a Wilcoxon signed rank test. Okay, so let's try to apply the Wilcoxon signed rank test. Now, there is something that I didn't tell you during my lecture. It's how you handle zeros. So if you recall, Wilcoxon signed rank test figures out how many of them are positives and how many of them are negatives, and you add up the ranks of those positives and negatives. But that means 0 cannot be included in your test statistics. So because of that, if you have a 0, you have to get rid of it. Okay? So you have to think of it as if this didn't exist. So you now just have n equals to 9. Because you're getting rid of the 0. And now you have 4, 7, 2. Okay, so you have all these numbers. And you list them from the smallest to the largest. So here's 1. And by the way, it's probably a good idea to leave a room for the rank. Okay, so you have 1 as the smallest value, then we have a 2, and then 3 appears 3 times, right? 3, 3, 3. And then 4 appears, and 5, 6, 7. That's what we have, right? Did I leave anything? I just wrote down all the numbers that appear in the B minus A from least to the largest, excluding the minus sign. We think about the minus sign later. I just wrote down from smallest to largest. Okay, since I have 9 data, this better be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I have 9. So I've put all of them, okay? And now we have to do the ranks. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the rank values. But this is a tie. In that case, what do? You take the average of the rank. So if you take the average, you get the rank value of 4. Okay? So now you can convert these raw scores into ranks. And the way we do it is first 4 has the rank score 6. 7 has the rank score 9. 0 we skip. 2 has the rank score 2. 3 has the rank score 4. 6 has the rank score of 8. 3 has the rank score of 4. 1 is 1. 5 is 7. Rank is 4. Okay. And then we compute t plus and t minus and take the minimum. Okay, so eventually we have to calculate minimum of t plus and t minus. Okay, we'll do that later, right? Okay, so let's do the 4 steps again. Step 1, H0 is that average of the 1 is bigger than, equal to the second. H alternative is that this is bigger than this other one. And then you have step 2. And this requires the table for the Wilcoxon. I forgot to bring it. Does anyone have it? Yeah. Okay, so for n equals to 9, what is the, what's the value?
8.
8 is, for 9, 8 is the value?
N equals 9 for a one-tailed test.
Yeah, one tail.
And alpha equals 0.5.
Yeah. So
Yes.
alpha equal to 0.05, and one tail requires 8. So the test statistic has to be 8. 8 or more. Okay. Is it 8?
Yeah, it's 8.
Okay. Oh, 8 or less, sorry. 8 or less. So if it's 8 or less, then it's heavily tilted to one or the other, so that it will reject the. If this happens, we reject the null hypothesis, right? So step 3. Now let's calculate t plus. So t plus, we add all the positive values and their rank score. So t plus will be 6 plus 9 plus 2, then 1 plus 7 plus 4. And that's 15, 25, 29. Okay, t minus. Okay, give me the t minuses. What are the values?
4, 8, 4.
4 plus 8 plus 4 plus.
That's it.
That's it. Okay. So that's 16. So the minimum of t plus and t minus is what?
16.
16. Okay. Since this is greater than 8, so it's not true that it's less or equal to 8. Again, step 4, fail to reject. And this is somewhat expected because t-test is a stronger test. Okay? If t-test can't reject the null, then Wilcoxon won't be able to reject the null. Okay? If t-test succeeds in rejecting the null, Wilcoxon still may fail, or Wilcoxon may be still able to reject the null if the data is pretty strong. Okay, so, but it's never the case that you fail to reject in the t-test, but you succeed in rejecting the null for the Wilcoxon. So if that happens, you've done something.